Oh, hey there. Welcome to AP Physics 2, Lecture 13-1, all about reflection and mirrors. That was a plane mirror, which is one of the types of mirrors we're going to be talking about today. In addition to curved mirrors, and we're going to be learning how to draw ray diagrams for both concave and convex mirrors. This corresponds to topics 13.1 and 13.2, according to the College Board course and exam description. And I highly recommend checking out the physicsclassroom.com reflection and mirrors simulations. Both the plane mirror images and the image formation ones are excellent. And this optic bench is one that just needs to be drilled into your brain. I recommend checking this out before you even come to this lecture and doing one of the optics bench activities. Okay, cool. So how does something like a plane mirror reflect? Okay. Well, on a plane mirror and on any mirror, it follows the law of reflection, which is that the incident angle will equal the reflected angle. And that is called the law of reflection. Now, an important thing to note is how we see anything, okay? In order for us to see something, anything, the light rays from that object have to reach our eyes, and that's called line of sight. So let's think about this for a plane mirror, okay? If we are looking, and this is our mirror, here I have my object. Every part of that object is sending off rays of light. So if we can imagine a ray of light coming from this tip of the arrow and hitting the mirror, if it reflects at just the right angle, it will hit our eyes, okay? Where the angle of reflection incidence equals that angle of reflection. Now, our eyes don't really know that our mirror was there. Our eyes just assume light travels in straight lines. That's how light travels. So our eyes would trace that image back and be like, oh, we see that here. And then we could do the same thing for a line at the bottom. In order for a ray coming from the bottom of that arrow to reach our eyes, it has to hit the mirror at a different spot and shine there and then reflect and meet our eyes. So if we trace that back, we can see the bottom of that arrow, okay? And it forms that object that seems to be, for us, behind the mirror, okay? To me, my face and my computer and the camera and everything that's there right now looks like it's behind that mirror. And we call that a virtual image, okay? So this is a virtual image. And for all images we create, we're going to be describing them using something called the lost art of image description. So L is for location, O is for the orientation, if it's upright or inverted, M is for or S is for the size or the magnification, and then T is for the type, if it's real or virtual. So for plane mirrors, something that happens with their location is because it's going to reflect at that equal angle, it's always going to look as if it came from behind the mirror. The image will always be behind the mirror for plane mirrors, okay? And have you ever seen a plane mirror flip you upside down? No? Okay. No, that doesn't make any sense. Okay, plane mirrors will always give you upright images, okay, that are the same size as the objects they are reflecting. They're not going to really distort the light because they're just reflecting at that equal angle. But since these light rays are diverging, okay, they're not converging to meet our eyes, that image seems to be behind the mirror, we call it a virtual image. Okay, cool? Okay, cool. So let's do some practice. This is really similar to that name your interact, or to the plane mirror interactive, what was it called? Who Can See Who on physicsclassroom.com if you want to try out more problems like this. But let's go ahead and see where our mirror images would be for each of these points and if they would be visible to our woman looking at herself in the mirror. Okay, so again, if we're thinking about point A, the light rays need to reach her eyes. Okay, I'm going to try to do this using a ruler so I can be as accurate as possible, which will be kind of hard in this situation, but we're going to try. So if I picture A, it's going to go and hit the mirror and then reflect at an equal angle to reach her eyes. Okay, so our eyes trace that image back. Okay. And so point A would show up behind the mirror. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, probably about right there. So let's see if I can fix up my diagram a bit. Okay, hit there. Our eyes trace back to that image, and then we can see where that reflection is actually coming from. Yep. So would she be able to see point A? Yeah, definitely. There is a line of sight between her eyes and the image that it would create. So A is possible. B, hopefully you guys can tell that point B would just be right there behind the mirror. So since that is within a line of sight, point B is definitely visible to her. Hey, if we trace that line of sight, okay, we can see that reflection. Yep. What about point C? So point C is about 3 spots away from the mirror. So its mirror image would be about right there. So would she be able to see this point? Okay, do we have a line of sight to that image? Let's check. So if we draw that line of sight, okay, yeah, we can see that an image could go from point C, reflect, and we can see that mirror image. Okay. And last but not least, point D, which would be way back over here. Do we have a line of sight to that one? Ooh, what do you know we do? Okay. We do have a line of sight to that image. Now, if we had a point that was, say, an image that was a little bit closer to the mirror, I'm going to go ahead and do point E, for example, there. We can see that there is not a line of sight that passes through the mirror. So there wouldn't be a reflecting ray that would hit the mirror and bounce off to reach her eyes. So E would not be visible, but A, B, C, D, and D all would be. So she could basically almost see her full body. How tall does a mirror need to be for you to see your whole body? Well, we can simplify it a little bit, okay? Let's go ahead and say that our eyes are at the very top of our head. They're not, but we can assume and ignore that 4 inches of forehead or whatever it is. So if we have eyes at the top of our head, okay, and we're looking at a mirror, what is the max angle that it would reflect and us be able to see our toes? Okay. Well, if those are our toes down there and we need a light ray to hit it, the ray from our toes would have to be able to hit the very bottom of that mirror to reflect at an equal angle up to our eyes. And that mirror would have to be hung so that it matches our eye line. Okay? So it needs to be exactly half your height, because then we could have an image from the shoes come off and hit our eyes. But note, it's only half your height if that mirror is hung at your exact height. If that mirror is hung a little too high for you, then you wouldn't be able to see your toes, even if it was half your height. Yep. So let's go ahead and do a little bit practice with tracing the path of light. So we have a 45-degree angle there. Now, anytime we do stuff in optics, we're going to measure our angles with respect to the normal line. So the normal line is a dotted line, or well, it's not a dotted line, I'm just drawing it as a dotted line, that is perpendicular to the surface that is hitting. So if I didn't draw that right, quite in the right spot, draw it more over here. Zip. Okay. This ray is going to come down and hit at that 45-degree angle. So if that angle, this angle is 45, okay, this is perpendicular to that, so they would be similar angles, okay, yep, picture that going down through there, that angle and that angle would be similar. So that angle is also going to be 45 degrees, okay? Or looking at it this way, this angle is 90. So it is going to reflect at a 45-degree angle. And come over here to hit that wall. Okay? So our angle of incidence has to equal our angle of reflection. Okay, so it hits that wall. We can draw in our new 90-degree line. So it hits that at that 45-degree angle and will thus reflect at a 45-degree angle and exit our wall. Okay, cool. Okay, cool. Let's go ahead and talk about curved mirrors. Okay. So if we are looking at the mirror from the concave side of it, the front of a spoon, if you will, that is a concave mirror. Where if we're looking at that curved outward, the back of a spoon part of it, that is going to be a convex mirror. Now, we have a couple things that we describe related to mirrors. Okay, the principal axis is the line that goes through the middle of the mirror. And it's typically where we'll draw our objects off of. So you can see that here and here. Okay. The focal point for a concave mirror is all parallel rays that hit it will reflect through that focal point. And for a convex mirror, they will diverge as if they came from that focal point, okay? So for a concave, parallel rays will all reflect through the focal point. Oh, and we call the focal point F. Where for a convex, okay, they will all reflect as if they came through it. Okay. So yeah, concave, parallel rays will all reflect through F. And then for convex, it is add those words as if reflected through F. Okay. Now, the center of curvature is kind of, is what it sounds like. It would be the center if we had a full spherical mirror. And it will also always be equal to 2F. Okay? We call it C, and it'll always be equal to 2F. Okay? That also together gives us our radius of curvature, which is the distance from the center to the middle of the mirror. Okay, so the center of curvature gives you that center, and the radius is the distance from that center to the mirror. Okay, that radius of curvature. Okay, the vertex is the spot where the mirror hits the principal axis. Okay, so that would be right there would be the vertex, and right there. And then, of course, the focal length is the distance from the focal point F to the mirror. Okay, now the focal length will have a positive value for concave mirrors, and for convex, since that focal point is behind the mirror, it will have a negative focal length. Okay, so what we need to be able to do is to draw ray diagrams and predict the images formed from concave and convex mirrors. So there are two main rays that we will always draw. We will draw one that goes parallel to the principal axis and then reflects through the focal point. And then if that is true, the reverse must be true. Something that goes through the focal point will reflect parallel to that axis. Okay, and then we draw those. The image will be at the intersection of those two reflected rays. Now, if you're having trouble with that and not very confident about where that image is, you can always draw an optional third ray, which is a straight one through the principal axis, okay, through the vertex, basically, okay, through the vertex. So let's go ahead and see what these mirrors and images actually look like. And we're going to be doing that with the PhET simulation. But again, I highly recommend you have already done this through that physicsclassroom.com simulation. But let's go ahead and look at what this actually looks like. Okay. So this is a ray diagram. We can show the marginal rays. Those are just showing those. The principal ones are those ones that I just talked about. Okay, here's for that plane mirror. We see our virtual images. Okay, if we added that second dot, okay, we can see where the bottom image rays are coming from, whether we have one or many coming out. So there are a lot involved in actually creating these images. But let's go ahead now and look at it for a concave mirror. And I'm going to go ahead and switch to an arrow because that is what we are going to use most often. Okay, don't need a second arrow. We'll just start with the first one. So if I have my object, okay, we can see there are a lot of places where that mirror will create an image. Okay. Our principal rays, we can see those. The one going parallel goes through that focal point. The one going through the focal point reflects parallel, and there's the optional third reflecting through the vertex. Okay, so let's go ahead and do some examples and analyze images at different object positions. Okay, starting with our concave mirrors. First, let's start with our object pretty far away. Okay, we can see as our object is far away, our image gets closer to that focal point, okay? And it'll actually stay between a value of 2 times that focal point and the focal point. So the location will be between F and 2F, or C. If we look at that image, it is real, meaning it's formed by those converging light rays. We could put it on a piece of paper and see that image if we wanted to, okay? So it's a real image and it is inverted, and it's also a bit smaller, okay? So it is inverted, it is reduced, and it is a real image. Now, I don't think I can actually get, oh, yes, I can. I have a ruler. So right now I have my focal length at or the diameter of the mirror, so that focal length is at 80 centimeters. So my radius of curvature should be at about 160, okay? So C is about right there. That's saying diameter, not the focal length. The focal length is about 85, it looks like, okay? So then 2 times 85, is that where that 180 comes from, right? Nope, 2 times 8 is 170. So our radius of curvature should be around there. Oh, and then our focal point's at 90. So if I put, there we go. That is the definition of C. I don't know why it doesn't have the focal length measured there, but it actually looks like the focal length is about 90. I read it as 85 earlier. I don't know how to read a ruler. So it's about 90. So then C or 2F would be at that 180, that radius of curvature. And we can see that if the object is there, the image is there, and it's going to be the exact same size. Yep. So here, that image would be at C. It is still inverted, but it is now the same size. And it is still real. It's formed by those converging light rays. Now, as we get closer to F, that image starts getting magnified. Okay, it's getting farther away and it's getting magnified. So farther away, it is still inverted, but now it is magnified. So you can see that pattern as that object moves farther away from the convex mirror, how that size changes. I want you guys to see those patterns there. Then, what if it's right at F? Okay. If it's right at F, do you see how these rays seem to be parallel? Okay. That's because no image forms at F. Okay. That's why I didn't put it in the chart, because no image forms there. You're just going to have those parallel rays going, and you're not going to get any image formation. But if we go in front of F, okay, now all of a sudden it becomes a magnifying mirror. And I highly recommend, if you've never tried this with a spoon, try it with a spoon. Start with it right up close in front of your face, and you should see a magnified virtual image of yourself behind that mirror. Like a magnifying mirror. If you have a magnifying mirror, this will work as well. And then as you gradually walk away from that, your image will disappear, and then it'll change into that real image. So if it's in front of C, our location is going to be behind the mirror, which makes it a virtual image. It is going to be magnified, and now it is upright. Okay, cool. Okay, cool. Let's go ahead and look at a convex mirror real quick. So if we look at that convex mirror, we can see that no matter where I put this object, okay, no matter where I put it, my image always is pretty similar. That image is always going to be behind the mirror, upright, reduced, and virtual. That is just how convex mirrors work, because they're dealing with all of those diverging rays. Okay? Those rays will never converge to create a real image. Our eyes will just trace them back to create that virtual image behind the mirror. Okay, cool. Okay, cool. So let's go ahead and practice drawing some of these ray diagrams on our own. You are definitely going to need a ruler for this, okay? Now, this is a little hard to do on the computer. I'm going to put my computer flat and do my best. But let's go ahead and see. So we should we're always going to just draw from the tip of the arrow so that we can locate the top of that image. So our first ray starts out going parallel and then reflects through that focal point. Our second ray that we draw will go through the focal point and reflect parallel. And our image is at the intersection of those two lines. So we can see that we have a reduced, inverted, and real image. Okay? Let's go ahead. We're going to do the math of it in our next section. Now, for this one, we're going to draw our ray parallel, and then it reflects through the focal point. And our second ray goes through that focal point and reflects parallel. And then our image is at the intersection of those rays. Okay, so we can see that I think it's actually a little bit bigger. And does that make sense for it being between C and F? Is that what we saw? Okay, between C and F, yeah, it should be magnified. So it is magnified, inverted, and real. It is formed from those two rays converging. Now let's go ahead and do one for one in front of a concave mirror. Now these ones are going to be a little more challenging because if you draw that parallel ray, you got to reflect it through the focal point. Oh no, yeah, we can reflect it through the focal point. Reflect it through the focal point. But, that's the ray that's a little tricky. Okay, we can't draw one coming from the focal point. So instead, that focal point is going to be behind it. So you're going to line up your ruler so that it goes through F and through the tip of that arrow. Okay, so up to there. Oh. Okay, that ray goes there. Reflects through the focal point. And then this one seems like it came from the focal point and it will reflect parallel. Now we can see that those two rays are diverging. They're never going to come back together. But our eyes don't know that they came from that image. Our eyes would trace those reflected rays back in a straight line. Okay, so make sure you are tracing the reflected rays. And we would assume the image is right there. Okay, so this is a magnified, upright, and virtual image since it's formed from those diverging rays. Yep. Now, for convex mirrors, okay, very similar, but just remember they're reflecting as if they came through those focal points. So we start out with parallel, okay, and then line your ruler up so that it's like in line with that focal point, and we have that reflected ray with the line of sight traced back. And then we go one, again, you're lining up your ruler with the tip of the arrow and that focal point, so it heads towards that, and then reflects parallel. And we trace that line of sight back to get an intersection right there. Yep. So it is reduced and upright and virtual. Okay, cool. Okay, cool. So, how does the math of all of this work out? Okay, what does the math look like for this? Well, let's go ahead and look at what that equation is. So, on our reference sheet that we get on the AP Physics 2 test, will be down here in optics. And this is the relationship for mirror images and object's images. It is that, I'm just going to screenshot it for us. Okay, 1 over S1 plus 1 over SO equals 1 over the focal length. Okay, so in this, SO is going to be the object distance. Why we use S's, I don't know. Okay, and SI is going to be the image distance. Okay, so what is that mathematical relationship? Okay, can we see it in the simulation? Okay, as our object gets farther away, our image approaches F. Okay, even there. Well, approaches like not being able to do an image. But as our object distance increases, our image distance decreases. And we can see that opposite relationship for both the concave mirrors and, different for convex mirrors. For convex mirrors, as that object distance increases, that virtual image distance would increase as well. So we do have some sign conventions when using this equation. Our object distance is what sets whether it's positive or negative, okay? The object distance is what tells you the positive side of the mirror, okay? Sets the positive side of the mirror, okay? So then for the image, okay, this gets a little bit confusing. Well, not really. If it's on the same side as the object, that's on the positive side of the mirror, and you have a real image. If it's behind the mirror, it's going to be a negative image distance. Since that's how we draw the focal lengths, like I said, we have positive focal length for concave mirrors and negative for convex. And for height, it tends to be positive for upright and negative for inverted. Though that's not in this equation. Okay, how do we find the height or that magnification of an object? We got another equation for that. It's going, we got another equation for that. On our reference sheet, we're still in that optics section. That next one is for capital M, the magnification. So the ratio of the image height to the object height is going to be the same as the ratio between the image distance and the object distance, okay? So those are going to be similar. They have the absolute values because it's a little hard to determine positive or negative for those. We typically have to draw it or just know our properties of mirrors. But the magnification of an object will always equal the, not the highlighter, I want my pen. Okay, M is for magnification. And then we have the image height and the image distance over the object height and the object distance. Okay, so we're always going to have to find the distances first. Okay, and then 2, it's the same ratio. Okay, and we can set up that. So we're going to practice it. We're going to go back and solve those ray diagram problems that we did initially. Okay. So for all of these problems, our object is 12 centimeters tall and is placed in front of a spherical mirror with a focal length of 18 centimeters. Okay. So let's go ahead and calculate the height and distance for this one when our image distance was at 58 centimeters. So again, that equation is 1 over the image distance plus 1 over the object distance, which is 58 centimeters, equals the 1 over the focal length, which the focal length for all of these mirrors is 18 centimeters. So 1 over 18 centimeters. So then we got to do some math. I got 1 divided by 18 minus 1 over 58, which tells me that 1 over S image is 0.0383. So then S image must be 1 divided by that, which is 26.1. And we said that it was reduced, or that 26.1, yep, that's in between F and C, so that checks out. So let's go ahead and find our height. Okay. That ratio is the height of the image over the height of the object equals the distance of the image over the distance of the object. So our image distance we just found is 26.1 centimeters. The object distance is 58 centimeters. And then the height of our object is 12 centimeters tall, okay, for all of them. So object is 12 centimeters. Easiest way, probably cross multiply and then divide, or we could do 26.1 divided by 58, and then multiply that by 12, and we get an image height of 5.4 centimeters. Which makes sense. We said it should be reduced, and that is reduced. And remember, this formula is in absolute values, so we don't worry about these signs there. Yep. So go ahead, pause the video, and try the rest of them yourself. Then come back and check your answers. So for the second one, we plug in that distance of 32 and that focal length of 18 to get an image distance of 41 centimeters and use that ratio to get a height of 15.4. And both of those match our estimations where it should be beyond C and magnified. For it in front, okay, that's where you might have gotten some negatives, so make sure that you're using those absolute values. But we get an image height of, that one should be negative 9 centimeters. Okay, it is a height of negative 9 centimeters because it's behind the mirror. And its height is 18 centimeters, so definitely bigger, magnified. Now, did you get the trick in the last one? Okay, it is convex, so that means the F is going to be negative. So it is negative 1 over 18 when figuring out our image distance, okay? If you didn't do that, you get 90. I know, because I made that mistake when first doing the calculation. And I'm like, that doesn't match my picture. Always check and make sure your answers make sense, because it's really easy to forget those little negative signs. But then your answers don't make sense. So that's your clue that you need to go back and fix it. Okay, so you get that negative 8.2 because our image is behind the mirror, and a height of 6.5 because it is reduced. Okay, cool. Okay, cool. So one last example problem. An object that is 5 centimeters high is placed 9 centimeters in front of a spherical convex mirror. The radius of curvature is 10 centimeters. Find the height of the image and distance from the mirror and describe it. Okay, so let's go ahead and draw what we have going on here. We got our principal axis. Okay, we got a curved mirror and it's placed in front of it. We got a 5 centimeter high object. So height of our object is going to be 5.0 centimeters. The distance of our object is 9 centimeters. And the radius of curvature of the mirror, so C, is 10 centimeters. Well, I need to know where F is, okay? F is really important. So we got to remember that C will always equal to F. So if we know the radius of curvature of our mirror, then we also know the radius and the focal length of that mirror. So we have our point F here, which is going to be at 5 centimeters, our point C somewhere out here. So then our object distance is going to be about right there. Okay, trying to draw it a little bit to scale, but you know, we're just doing a little sketch here. Okay, sketch our principal rays. We go through and whoop, not perfect, but that's okay. Through that focal point, reflect and parallel, and we get our image. Okay, so from just our quick little sketch, we can see that our image is inverted and real because it's formed from those converging rays. I think it looks a little bit magnified. We will check that in our calculation, but I think it looks a little magnified. And if I remember right from our optics bench and we're picturing it on our head, I believe it should be a little magnified. Let's go ahead and find its distance from the mirror and its height. So let's start with the distance. We have 1 over the image distance plus 1 over the object distance equals 1 over the focal length. So doing the algebra, we have 1 over 5 minus 1 over 9. And then we take the inverse of that, so 1 divided by that. And we get an image distance of 11.25. Okay, we just had 2 digits there, so we're fine with just saying 11 centimeters. And then if we want to do our height, okay, for height, it is the height of the image over the height of the object, which is 5 centimeters, equals the image distance over the object distance. Okay, so we have 11 divided by 9 times 5, or you could think of it as 55 divided by 9. Okay, either way, we get an image height of about 6.1 centimeters. So yes, it is a little magnified, and our calculations support our model in our picture. And that's it for mirrors. Okay, cool? Okay, cool.